Okay. Um, I think. Okay, we're live. Thank you everybody for coming online. We're live streaming both on. Okay, I can hear myself. Sorry about that. We're live streaming both on YouTube and Facebook this time. I see someone in the chat room already. Hi, Alice. And my name is Xiyang, for those who don't know me. Today, we're fortunate to have Maruan from Carnegie Mellon University to talk about his research on zero-shot machine translation. Maruan Al-Shadivat is a PhD student in machine learning at Carnegie Mellon University. He has previously worked at OpenAI and Google Research. His research interest includes sequential decision making, multitask learning, deep learning, graphical models, interpretable machine learning applications in healthcare, natural language, multi-agent systems, and general AI. So, without further ado, I'll give the mic to Maruan and let him speak about his recent research work on consistency by agreement for zero-shot neural machine translation.
Which is based on the paper that appeared at NACL earlier this year. And this is based on work that I did at Google last year with Ankur Parikh. So broadly speaking, this is going to be focused on neural machine translation, which stands for translation between texts in different languages, and we're going to focus on multilingual setting. But in general, the ideas that we develop in the paper, the machine learning ideas, are broadly applicable to other types of translation tasks. For instance, there could be translation between different, different images. Maybe you're familiar with CycleGAN and these types of architectures. So we actually haven't used this approach on these tasks yet, but I think that the methods could be broadly applicable and be interesting to see where we can take them next. So this will be like some parts of the talk are going to be pretty technical. I'll dive into just in a bit, but feel free to ask questions throughout the talk. There'll be multiple parts. I can pause and answer questions as needed. Okay. All right. So so this is the outline of the talk. I'm going to focus on 4 points today. First one being what is zero-shot translation and why do we care? Why is it important? Then I'm going to go and introduce the notion of zero-shot consistency of a machine translation model or machine translation system. And then I'll discuss a bunch of methods that are consistent or not consistent with respect to this notion or metric. And then I'll tell you about our proposed method, which is called agreement-based learning for multilingual NMT. And finally, we're going to discuss some results, experimental results on different data sets that we obtained. Right. So let's dive in right into the setup. So in the standard bilingual translation, we're given let's say 2 languages. Here I denote them as nodes in the graph, and we'd like to learn a translation model that is able to sort of transduce sentences from one language into sentences in the other language that have the same meaning. So we can approach this problem as a supervised translation problem and just train 2 supervised models, one for each direction. So the problem becomes more challenging when we have n languages, as the number of directions in which we would like to train the model to translate becomes n squared. And this is challenging because just training a single strong bilingual neural machine translation model requires first a lot of compute. Often we need to train the model for weeks, and moreover, it requires a lot of parallel data in order to get a good model. But oftentimes we don't have access to all the data or large amounts of data for each single direction. Typically, we have access only to a subset of pairs of languages for which we have parallel data. And why is that the case? Well, if you look at where the data is coming from the internet, and we can look at the distribution of languages of content of the internet, you can see that there's a lot of content in English, and there is some content in other languages, which is much fewer contents, but also like there's a long tail of languages for which we don't have much content at all. And then maybe there is some overlap between English and these kind of rare languages, but it's unlikely to find a lot of resource in terms of parallel sentences between these rare languages themselves. So oftentimes we'd be in a sort of situation where we have parallel corpora between English and other languages, but maybe not so much or almost no content overlap between other languages in the graph. So the question is, how do we train a neural machine translation system that is multilingual and supports translation in all of these directions, but only having access to a subset of the directions, a pretty small subset of the directions? And how do we ensure that the performance of this model, being trained only on a subset of the directions, sort of stays competitive along the directions for which we don't have data at all? Right, so let's formalize this a little bit more. So we're going to use this graph throughout the presentation. We'll call this graph on the left part of the slide the translation graph. And nodes correspond to languages, edges correspond to directions, and then we'll also denote edges with solid black as the edges for which we have parallel data. And we denote edges in dotted red as edges for which we don't have parallel data, or we don't have any parallel data at all. We're also going to denote it as calligraphic ES and E not in our notation throughout the talk. And again, the goal is to try to learn something from these sort of supervised directions and then perform well on all the directions simultaneously. So I'd like to get a single model that performs really well in all of the directions. So the question, how do we approach this problem in the first place? To understand how we do that, we can look at just different components of the machine translation system. And on the slides, I just outlined three key components. It's the data that we feed in, that we train the model on, and the model itself, or the architecture that is being trained, and then finally the loss, or the thing that we optimize in order to search for a good architecture or a good set of parameters. So there are papers and works that try to tackle each of these components. For instance, you can tackle the data component and try to expand your data set, not only so that it not only has the supervised pairs from the supervised directions, but also you somehow enrich this data. Maybe you add some monolingual data, you generate a bunch of synthetic data for these zero-shot directions using back translation, and then you try to retrain your model on new and enriched data sets. And there's like a lot of work that's been done in this direction over the years. There's some recent work that also occurred at NAACL, which is pretty interesting, but this is not the component that we consider in our work. And so we don't do anything with the data. So on the other hand, there are works that try to tackle this model architecture approach. And the idea is to enable some sort of parameter sharing between the models, the supervised models that you train to translate between different directions. Perhaps one of the most notable recent works, is by Melvin Johnson and others. You might be familiar with this paper. It's called Google's Multilingual Neural Machine Translation that came out in 2017. And it's a variation, it's a pretty simple variation, pretty elegant variation of the standard seek-to-seek model, or encoder-decoder architecture. That basically shares parameters across all the directions. There are other variations where you can share only subsets of parameters, or maybe you not only share parameters, but you also condition on the pair of languages that you want to translate between, and then generate parameters for certain components of your model. Let's say you generate parameters for your encoder, so that this encoder is specifically good for this pair of languages. So let's look a bit deeper into how this architecture works, because our work is primarily based on the Johnson and others architecture. So just one slide summary of what encoder-decoder architecture looks like. I'm assuming that the audience is familiar with most basics of neural machine translation, or seq-to-seq. If you're not familiar, feel free to look it up somewhere, maybe on Wikipedia, or just Google seq-to-seq or encoder-decoder architecture. You'll see a lot of nice blog posts, tutorials, and as well as references. But it's been used throughout the years in many works. The idea is that if we would like to translate between two sentences, let's say one of them is in English and the other one is in German, we would take a sequence of tokens in English, we're gonna pre-process them and then push them through an encoder that will return us a sequence of vectors that will represent, each vector will represent the corresponding token and in the context of the entire sentence. And so this is some sort of contextualized representation, and then we're going to try to attend to these representations that we got from the encoder, and then try to decode words or tokens one by one. So we're going to start with the starting symbol of the sentence, and we're going to try to predict the next symbol and then refeed it back in, and predict the next symbol, repeat it back in, and every time whenever we're trying to predict the next symbol, we'll also attend, or I'm not going to go into the details, but mathematically account or condition on this contextualized input sequence of vectors. So now, how do we make this architecture that works for a pair of languages work for multiple languages? This is the key idea proposed by Johnson and others, is that now instead of just feeding in sentences, let's also denote the target language that we want to translate the sentence into. And in this case, we can prepend a tag that denotes to and then the language representation. In this case, to German. Tag will prepend to the English sentence, and now we're going to encode the whole thing again. And then we're going to get a representation that is not only just contextualized for English, but also sort of suitable for decoding into German. So we're going to use the same encoder, which is going to prepend this tag to the sentence. We're going to use the same decoder and try to decode by conditioning on this representation that is suitable for decoding into German. And then given that we try to do this and to try to train the model on all sorts of all pairs of languages that we have in our training data, the decoder will learn that when the representation is has been produced for specifically decoding into German, it will figure out that it needs to decode in German. And if it's another language that we pretended the representation of this other difference, will decode into the other language. Basically, the parameters of the encoder and the decoder stay the same. The only neat trick is that you need just to prepend certain tags to the inputs of the model, and you'll be able to translate between different directions. Yeah, quick note that the vocabulary in this case should be shared. There are other works and approaches that try to decouple vocabularies. This model sometimes could suffer from trying to decode into a different language than the one that it was asked to, or maybe mix some of the words. But I'm not going to go into these details today. So does this approach actually work in terms of zero-shot performance? Well, it turns out it does. So on the slide, you see the table excerpt from a recent paper that tries to look at a data set of 3 languages: English, French, and Spanish. Oh, sorry, English, French, Spanish, and Russian. In this case, and then they look at the performance along the supervised directions, and then they show that actually there is a non-zero performance along the zero-shot directions. It's not the original paper that proposed the architecture. It's one of the follow-up papers. But just as an example, I'm showing the table from their paper. And then if you look actually at the model that was trained not only on the supervised directions, but also on the zero-shot directions. So the model has been trained on all the available data in the data set. You could see that, in fact, there is a non-trivial improvement in performance. So while zero-shot model, while the neural machine translation model that is trained only on some supervised directions has a non-zero performance on zero shot, it is nowhere near close to something that would be desirable or useful in practice. So we still need to have data along certain directions in order to make it useful. And this is not just the observation of that paper, that also was observed in other work. And you can see another table from also a recent paper from EMNLP 2018. And you can see that there's a huge discrepancy between the performance in supervised and zero-shot directions as always. So the question is, like, how do we, why does this happen? Do we need to change the architecture? Do we need to change the training algorithm? Do we need more data? Remember that the constraint is that we don't have access to the data along the zero-shot directions. So the only thing that we can affect is maybe collect more data along the supervised directions, maybe do something with it. And in order to understand what exactly we need, in this case, we try to introduce this notion of zero-shot consistency of machine translation models that I'll go right into. But I'll pause for a second just to see if there are any questions or clarifications. No questions? Okay. All right. All right. So what is zero-shot consistency? So I'll introduce this notion through a sketch that would make it hopefully intuitive. So so imagine you're training your multilingual neural machine translation system. And then along the x-axis, you have some iterations, and then along the y-axis, you have your score. Let's say it's a blue score. And you just measure this blue performance averaged across all the supervised directions. So this curve will keep growing as with the iterations. Now, if you look at the typical zero-shot performance, so you train this architecture proposed by Johnson and others on some public data sets, you'd see that initially the zero-shot performance, or the average blue across the zero-shot directions, keeps increasing, and then at some point it saturates and just plateaus, and keeps oscillating. And also, interestingly, if you keep rerunning this thing multiple times, it will plateau at different points. So, but it always plateaus, and there's always this gap where supervised directions keep improving, while zero-shot direction is actually plateaued somewhere like at the beginning of training, so it doesn't really benefit from the improvement or further training. And what we would like to see, though, right, is as we train the model over time, I would like to see that the model is consistently improving in terms of the zero-shot performance. Right. So even though we're training on supervised directions, we still would like to see that there is some sort of non-trivial transfer that is happening from the supervised to the zero-shot directions. And this gap is not growing, or somehow the gap is sort of under control. It's not like uncontrollably growing, where supervised directions are the best, and then zero-shot performance is somehow random, near random, or not good enough. So to quantify this, we introduce this notion of zero-shot consistency, where we say that machine translation system is zero-shot consistent when, and then we assume that the maximum loss across all supervised directions, if the maximum loss across all the supervised directions is bounded by some epsilon, and here L is the loss of the model, right, on with expected loss with respect to parallel sentences that are selected from these directions I and J, right, in our graph. So we assume that if this is bounded, then if the model is consistent, if this implies that the zero-shot error is going to be also bounded. And again, to parse this equation, again, we have this expected loss of the model, but now on the zero-shot directions. So basically, what we're saying that if the loss on supervised directions is small, right, and it's bounded by some epsilon, it should imply that the loss on the loss on the zero-shot direction should be also somehow small. It may not be bounded by the same epsilon, but it could be bounded by some function that is, by a function kappa of epsilon. And importantly, kappa should go to 0 as epsilon goes to 0. this is the definition of zero-shot consistency, meaning that if the model was trained to completion, basically to perfect performance along the supervised directions, it should imply that along the zero-shot directions, the model should be also perfect. Right? And then if the model isn't perfect, then by how much it is imperfect on supervised directions should be should imply how much imperfect it is along the zero-shot directions. Okay, so the question that we asked next is, can we use this notion of zero-shot consistency to look at the previous work and see whether any of the previous methods are actually zero-shot consistent? And it turns out there are, and there are pretty famous methods that are. So the first one, the first consistent method, is called pivoting or bridging, where instead of directly translating, instead of having a single system that directly translates between any pair of languages, we're going to introduce an intermediate language. So let's look at this example where the intermediate language is English. So whenever we'd like to translate between German, let's say, and French, and in the training data, we don't have any parallel data between German and French, but we do have training data between German and English and English and French. We can train two supervised models and just station them together, right? And then whenever we'd like to translate from German to French, we're going to first translate into English, then translate into French. So this is a very strong baseline, and it's a go-to approach. So usually it works pretty well in practice. What we prove in the paper, so after introducing this zero-shot consistency formally, we can formally prove that pivoting is actually zero-shot consistent under some mild assumption on the quality of the supervised directions. And so intuitively, if the supervised models are really good, then by just pipelining two models together, the eventual translation will not be too bad. One of the disadvantages, or there are a couple of disadvantages. So first of all, inference time is twice as slow because we need to run the translation twice. And again, pivoting is finicky because if the models are not up to par, and we'll see this in some of the results, the performance can suffer. So the pipelining errors will accumulate, and then if you need to pivot a couple of times in order to get from one language to the other, then even though we haven't tried these experiments, the errors would accumulate. That's what this theory says. Okay, so there is another method called distillation, and was also introduced in the literature, trying to tackle the same zero-shot performance problem. So the idea here is that the setup is the same. We have two supervised directions, and we would like to learn how to translate between the zero-shot directions. And the idea is that first we can augment data, right? We can generate outputs, so we can look at all the German to English parallel sentences, and for all these parallel sentences, use a supervised model to generate a French sentence, so that we have a not only parallel sentences, but we'll have a parallel sentence and a synthetic good translation into the third language. And then we can try to train a model that goes directly from German to French, and it tries to imitate or distill. We try to distill a model along this sort of zero-shot direction so that it imitates the supervised model pretty well. And we can do the same thing in the other direction. So that's a pretty competitive baseline. We also prove that distillation is zero-shot consistent under mild assumptions, again on the supervised directions. It's pretty efficient. It works pretty well. One of the disadvantages, though, is that given it works for a specific direction only, right? So if we have a bunch of zero-shot directions, for every single direction, we'd have to go and distill the model. If we would like to have a system with a multilingual system that shares parameters across all the directions, then just running distillation on one of the directions can somehow unpredictably affect supervised directions or other zero-shot directions. And so it's if you have one specific zero-shot direction in mind, then probably using this approach is good. But if you have a consistent sort of multilingual system, then it would be challenging to use this method. Okay, so now I'm going to go into our proposal, the key proposal in the paper for the agreement-based learning that tries to, sort of rectify these disadvantages and be the go-to method that actually allows you to learn multilingual NMT models that are consistent across all the zero-shot directions, as well as they maintain performance along the supervised directions.
Mario,
Are there? Mhm.
do uh, we have a question about, I think, about the bound. Do you want to take it now or later?
Sure, I can. Yeah, yeah.
Okay.
Right now is good.
So the question is, what? I'm not sure. What is kappa not bounded? I'm not sure what that means. I think she's asking why. Oh, so she's asking, wouldn't there be a possibility? Oh, what if? Oh, thank you. What if kappa is not bounded? Wouldn't there be a possibility that kappa is exponential by a compounding error?
Right. So I'll go back to, I guess, the slide. Right. So this is just the definition of zero-shot consistency. This is like how we define how we would like our model to be, right? So for certain methods, yes, kappa will be unbounded. And as we will see, well, I will not formally show it, but I'll just argue intuitively that if you take your standard multilingual NMT with these prepended tags and then you try to optimize the standard loss function, there is no guarantee on the kappa, right? The kappa can be arbitrary along the zero-shot directions, and then there will be no relationship between the bounds on the error here and bounds on the supervised directions. So technically, yeah, but we would say in that case, by definition, such model or such approach or such machine translation system is not zero-shot consistent. If you can show that the kappa is like unbounded or growing somehow differently, or even if the very last condition where kappa doesn't go to zero if epsilon goes to zero,
Okay,
right?
thank you.
Okay. All right. So I'm going to go now into. So I discussed a couple of methods from the previous work. I showed that they are zero-shot consistent. Can we do better in terms of sort of providing a coherent framework for learning multilingual machine translation systems? And to do so, we decided to tackle the very last component of the MT system, which is the loss. From the machine learning literature, we know that the loss is a very important aspect of any machine learning system, because it's sort of the properties of the resulting model often would depend on the loss that you're trying to optimize. And I'll try to show you in the following slides why and how. Okay. Right. So, going back to our multilingual graph, we can reformulate our machine translation system from a probabilistic perspective. From a probabilistic perspective, we have sentences, which are equivalent sentences that are different representations of the meaning, right? So, which means that given some sort of meaning, we can have representation of that meaning in k different languages, and then this meaning will be represented by k different sentences in the corresponding languages. Now, our goal of learning a multilingual translation system is actually, from a probabilistic perspective, can be seen as learning this joint probability distribution, so that it assigns very high probabilities only to tuples of sentences, k sentences, that are all sort of equivalent, have equivalent meaning. Right? So again, if we would like to learn this model, we can construct a loss, and the ideal loss that from a statistics perspective, it would be the full likelihood, right? We're trying to optimize or find a model such that it sort of assigns very high probability to the sentences that are equivalent, and then even if one sentence is sort of not equivalent to the other sentences, the log likelihood of the corresponding tuple will be lower. So we can use this loss technically to optimize, to search, or like to optimize the model. The problem, though, is in the zero-shot setup. Right? We never have access to k tuples of equivalent sentences. We assume that we only have parallel sentences, bilingual parallel sentences, meaning that from among these tuples of k, we'll be getting only a pair of sentences, and we will not have data for the rest k minus 2. Right, so this is problematic because that doesn't allow us to even construct or compute this loss. Okay. Even if we wanted to learn the model using this loss. So the standard approach to overcoming this problem, again from a probabilistic perspective, is just ignore certain directions in our model. So the directions for which we don't have data, let's just ignore them. Let's just focus specifically on the conditional probabilities that correspond to translation directions. So in this case, this conditional probability corresponds to the model that translates from language I to language J, so from English to French. And then we're going to go in the sum across all the supervised directions. And then in the inner sum, we're going to go through all the sentences for that specific supervised direction. So, this is called, in the statistical literature, the composite likelihood, because you basically compose a surrogate objective that tries to approximate the likelihood out of pieces and blocks. So you assume that all these pieces are independent, and you just compose this joint objective, all the rows. So the problem with this objective, and even though this is exactly the objective that is used, that was used by Johnson and others, and many other multilingual neural machine translation approaches, this specific objective has a disadvantage, right? It is consistent across the supervised directions. And by optimizing this objective, you'll definitely reach a model that is good along the supervised directions, but it has no statistical guarantees along the unsupervised directions. And just to give you the intuition, so imagine I give you a model that is nearly perfect along all the supervised directions, but then the same model just outputs garbage across the zero-shot directions. So you provided French, they ask you to translate into Russian, and it just outputs incomprehensible sequence of tokens. So with respect to this loss, this model that I just described is going to have a very low composite likelihood loss, right? Because the loss actually is insensitive to any errors along the zero-shot directions. So it means that if you optimize this loss and then you attain some sort of local optimum, right? That local optimum will have no guarantees with respect to the zero-shot directions, which is unfortunate. And that's why the model that we would obtain will not be consistent with respect to the notion of consistency that we introduced before. Okay, but that's the intuition. Now, how can we actually improve upon these lessons? How can we construct an objective that actually would account for zero-shot directions? So let's take a look at an example where we're trying to translate between English and French, and we have parallel data for these two languages. And we know that in the system we have a bunch of other languages. So for instance, we know that we have German in there. Right? We'd like to build a system that not only translates between these two, but also between other languages, and we know that there is some German language. So we can write down the composite likelihood terms as given on the slides. Right? For translation from English to French and from French to English. But then we can expand each of the terms and then sort of marginalize out some representation of the German sentence. This is the standard procedure in the the probability theory, where you say that your distribution is actually equal to it is just the equality, where you just marginalize out some unobserved variable. Right? If you sum across all possible translations in the German under this model, this would be exactly equivalent to the original log probability, log conditional probability. So the thing to note here is that the translations into this latent language that we introduced, right? These translations are independent. So we assume that when we translate from English to French, for instance, right, we can technically also translate from English to German and then try to marginalize out this German token, right? But we do the same when we translate from French to English. But there's sort of no connection between the two. So the idea is that we could try to enforce actually these latent representations to agree with each other, and that's why the objective is called agreement-based. So it was inspired by previous work on agreement-based learning. and we construct an objective now instead of having sort of independent latent representations. We just manually force them to be exactly the same representation. Right. So mathematically or like mechanically, you can think of this as swapping the sum and the product. So this product and the sum. If we do that, we'll arrive at a different objective. Right. So it has a natural probabilistic interpretation that not only would try to maximize the joint probability that the model sort of generates, generates correct French sentence given the observed English, and vice versa, but at the same time, right, it generates the same latent representations. And technically, these latent representations don't even have to be, sentences in some third language. Maybe if you had multimodal data and then you try to learn to translate between English and French, maybe there were also images or, I don't know, audio signals or something. You could try to make sure to align them to sort of align this third modality of the data somewhere in the latent space and enforce this consistency by slightly changing the objective function. Most importantly, we can rewrite this thing is actually a composite likelihood, right? So the composite likelihood terms and an additional agreement term that enforces this agreement of the models in terms of the latent representation. Right, so this is precisely the relationship between the left-hand side, the standard composite likelihood, and the new loss where we swapped the sum and the product. Okay, so how do we use this loss? How do we train using this loss? So on the left-hand side of the slide, you can see that an example where we're given parallel data between English and German, and then English and French. And while we're training, so for these blue nodes, we can compute the standard loss, right? The standard composite likelihood terms. But every time we get a pair of sentences, let's say in German and English, we can also compute the agreement term between the two and impose this additional loss. And whenever we get a pair of sentences, English and French, we're going to compute the agreement loss in the German space. Right? And by these subscripts, I mean that this translation or latent translation came from French, so it's German translated from French, or German translated from English. And that's intuitively how it would work. So when we train the model, we're going to construct these losses. And the loss, this regularization or agreement terms will depend on which pair is actually supervised and which pair, and which language is latent language. Okay, so on the theoretical side, we do prove that agreement-based learning yields zero-shot consistent models across all directions. And this is nice because basically, if you compare it to previous approaches, you sort of end up having to train a single system, a single model that will have much better or better performance along the zero-shot directions without the need to either select the zero-shot directions and distill between the supervised and zero-shot models, without the need to pipeline together different models. So that's the huge advantage of the approach. Now, in order to compute, so one problem with this agreement term that I haven't mentioned yet, but is basically the sum, right? So the sum is really problematic because you have to sum across all possible, translations and all possible basically sentences or sequences in this, latent space, and all possible sort of sentences in the German, let's say. And this is infeasible. It's combinatorially infeasible, so we have to approximate this term. And what we do to approximate this term, first of all, we lower bound the agreement term using the Jensen's inequality, and then instead of computing the sum, we convert this into computing two expectations, and these expectations are further approximated by sampling from the corresponding translation models. So whenever we'd like to compute the loss, let's say between German translated from English and German translated to French, we're going to sample from, we're going to condition on French, we're going to run the model to translate into German. We're going to do the same thing here. We're going to condition English. We're going to run the model to translate into German. and then we try to enforce this agreement between the samples. And so that will be the approximation of this expectation. So first lower bound, then we approximate the expectations. Now the other thing is that we can have more than 3 languages in the system. We can have 5, 6, 10, 100, and in that case, technically we should be able to compute agreements whenever we're given a pair of sentences. We can technically compute agreement in k minus 2 possible latent representations, and this could be very computationally problematic, because even to compute a single agreement term for a single latent representation would add a bit of computational overhead. We don't want to multiply that computational overhead by, let's say, k minus 2. Instead of doing that, we subsample at random, uniformly at random, during training, one latent representation in which we try to agree. Let's say we have 4 languages in the system. We've got a pair of supervised sentences. Now we're going to randomly select from the other pair of languages which one we're going to be agreeing on for the specific pair, and we're going to randomly, resubsample while we're training. So in expectation, this will approximate as if we were sort of selecting and trying to agree on all the sentences. And finally, you should look into the details in the paper or the code that we have publicly released, but it's greedy continuous decoding that allows us to back propagate through these translations. Okay. So I'm going to walk through the computation graph to sort of build a little bit of intuition, but it's not necessary to understand it all. But the idea is that we start, let's say, with the initial sentences, let's say in English and French. We'd like to translate the French sentence into English, the English sentence into French. We're going to pre-process them and get subword tokens. We're going to compute embeddings, then encode, and then we get some sort of representation, right, that corresponds to the encoding suitable for decoding into the corresponding target language. Okay. Now, to construct the loss, so we're going to compute these representations both for English and French, as if we were translating each of these sentences into Spanish, for instance. Then we're going to decode them and actually obtain translations from English to Spanish and from French to Spanish. Right? And then we're going to get these decoded embeddings for the Spanish latent translations. And then in order to compute the agreement terms, we'll have to run the decoder again. And this intermediate decoder is running greedily, a sort of continuous decoding, which I'm not going to go into. And then this final decoder is going to be running with teacher forcing, right, in order to compute this cross terms, basically, of agreement, right, of the log probability of the Spanish translation from French under English, and then similarly log probability of Spanish translation from English under the model that translates from English or from French to Spanish. Right, and this will give us the symmetric agreement loss, which sort of somewhat reminiscent of the Kullback fragment divergence if you look closer. Okay, so not really going into the details of implementation here. I would like to mention that this loss is just a constant factor of computational overhead for us. So we need to run encoder a couple of extra times, and then we need to run the decoder a couple of extra times. So overall, it's a factor of around 6, slightly less actually, because we don't need to run the encoder only 2 times, and then the decoder runs 4 extra times. Yeah, so also the entire thing is parallelizable across multiple GPUs. So if you have multiple GPUs, you can actually compute agreement based terms on different GPUs, and technically it should not result into any computational overhead. In our experiments, we didn't do that. We just ran our models, we trained our models on a single GPU. Okay, so now I'm going to go into experimental results. I think I am a bit lacking on time, but if you have any questions, you can either ask now or maybe you can wait until the end of the presentation.
We have one question.
Mm-hmm.
So is the model assumption based is the assumption of the model that languages are independent to each other?
So model technically does not assume that the languages are independent to each other. So it's hard to say. Like we assume that there is some sort of meaning and some latent space of meaning, and then given that meaning, we have different representation of that meaning in different languages, right? And this is what the probabilistic model assumes. It tries to learn this joint probability distribution across all the meanings together, so that all the meanings are sort of consistent in each of the language. Right. So we don't assume any independence, if I understand the question correctly, between the languages themselves. Neither we assume the independence between the sentences, because if sentences were independent, then there is no way to try to translate, from source to target or from source to auxiliary. The only thing that the model assumes is actually whenever we generate the auxiliary or the latent translation in some third modality, or we call it auxiliary modality, in that case, we assume that they should match precisely. And that's why we have this agreement-based loss that tries to match these two.
Okay, she added she meant from the conditional probability.
I don't think I understand like which conditional probability, but maybe I can come back to this question.
Okay.
Yeah. Okay, so in terms of experimental results, we looked at actually 5 data sets, which we tried to be as comprehensive as possible, and we tried to make sure that all the data sets are publicly, public data sets, so that people can, play around and do further research on these data sets. So 2 of these data sets are coming from the previous work by Sistorian and others. We just again replicated the setup. It's based on the UN corpus, right, with 3 languages or 4 languages. We have about 1 million parallel sentences per pair in this case, and the multi-parallel data was cleaned. So if you look at UN corpus, you notice that actually it's a multi-parallel corpus, meaning that for every single sentence in each language, you have translations into all other languages. So this is not the setup that we considered, so we'd like to avoid it. So when we constructed, when the training set is constructed, this multi-parallel data is sort of cleaned. Similarly for Europarl, where the multi-parallel sentences were cleaned, and also this data set appeared in previous work. And finally, IWSLP, which is much smaller data sets from a different domain. The previous 3 are from formal language. IWSLP is from a spoken language from TED Talks. It had 6 languages. It's much smaller in terms of parallel data. And interestingly, the original data set that appeared with competition had a lot of multi-parallel data, so we had to clean it as well. We'll see that it actually, the official data set is not particularly suitable for evaluation of zero-shot performance, because this multi-parallel data affects the model a lot. So sometimes you can actually train your model sort of on the supervised directions, but because of this multi-parallel data, the model learns, picks up certain correlations pretty easily, and then performance on zero-shot directions might be even better than on supervised directions, which is not what you'll typically expect. Anyway, so we constructed the IWSLP star dataset, which is a clean version, and it's right now it's available publicly, so you can download and preprocess and get this dataset. So in terms of results, I'm going to look just out of here. You can take a look at the paper to see the whole comprehensive tables. So the first result is on the UN Corpus 2, and we measure the average supervised performance, as well as performance on all possible zero-shot directions. And then we have a couple of baselines. So the original baseline, the numbers are taken from the previous work, which is dual zero. It's called dual null machine translation model that tried to use some sort of distillation additional tricks to improve zero-shot performance. There's basic, which is the basic model of Johnson and others, and then there's pivoting, it's a very competitive baseline, as well as agree, which stands for our method. And we notice that, first of all, agreement-based learning does not result in any loss in performance on the supervised directions, while if you use dual, or if you try to optimize for zero-shot performance specifically, you often lose quite a bit in terms of performance in the supervised directions, right? But also we notice that agreement-based learning performs very, very competitively compared to pivoting, while the pivoting is the gold standard. It's widely used. We still see that we can either surpass in certain cases or be on par with pivoting. Now, if we look at the IWSLT results, so two things. I'm just showing plots for IWSLT, the original data set, which had 16 supervised for zero-shot directions, and our clean version, where we had only 8 supervised and 12 zero-shot directions. And the difference that you notice is actually, the thing that you notice right away is that the basic model on zero-shot directions, on average, is much better than pivoting, which was pretty surprising. If you look at specific zero-shot performance on specific, like on each of these 4 zero-shot directions, you can see that on some of the directions, the model performs better than on some of the supervised directions, which was also surprising. So there are papers in the literature that discuss this phenomenon on this data set, and they argue that it's probably not the best data set to use for zero-shot machine translation. We try to clean it, and after that, we see with the reversal of the trend. Basically, pivoting is again the best if you just myopically train your model on the standard loss. There is a huge gap between the two, which is as expected, and then agreement actually improves upon that and adds like about 3 blue points. Yeah, I guess one thing to note is that maybe there's probably no good way to compare between these two data sets. They're slightly different also because after cleaning the data from this multi-parallel, we had to reduce the size of the data set significantly. So that's something to take into account. And then finally, we ran a bunch of experiments in the limited parallel data regime. So basically, these plots are performance of the methods on different directions on the Europarl. All of these directions are zero-shot that are given on this slide. And then we train the model. So let's say each slice of each graph is when we train the model for a bunch of iterations until convergence. And then we measure the performance of this model, but we train on a subset of available training data. So let's say we trained on 100,000 or 100,000 parallel sentences in each of the supervised directions, and then we look at the performance. So in certain cases, we see that there is no difference between the pivoting and agreement. They're almost identical in terms of German to Spanish or German to French. The baseline, the basic method is always subpar, but in certain cases, we see that zero-shot performance, while general, it improves with the amount of data, right? We see that the basic method sort of saturates at some point, and then it stops improving on the zero-shot directions. Both pivoting and zero-shot are consistent methods, and they keep improving as the amount of data increases. In this case, not with the iterations of the training iterations, but with the amount of the available training data. So the quality of pivoting sometimes, depends on the quality, or it highly depends on the quality of the supervised direction. So we see that sometimes it's better, sometimes it's worse in agreement, and agreement-based performance is sort of more stable across the different directions. That's what we noticed from these experiments. Okay, so just in summary, we introduced the notion of zero-shot consistency. It connects supervised and zero-shot performance, introduced the agreement-based learning, and we ran a bunch of experiments on our data sets, so we made everything publicly available. For more details on the architecture, the training, and then you can look into our paper as well as check out the code. I'll stop here and probably take a few more questions. I think we have 5 more minutes. Mm-hmm.
It's
Sorry,
go ahead.
Yeah, I can maybe discuss a bit more potential future directions if there are no questions. But yeah.
Okay.
just let me know.
So it's still that so there were some discussion about the previous question, but
Hmm.
I think we can wait till like later.
Okay. Okay. Yeah. So what are the next steps? You might ask like, what are the limitations? Maybe what is the related work or the open questions? And there's been a couple of concurrent works with my work. So one of them is it's called the missing ingredient of multimodal machine translation. And the idea is that so while we enforce the agreement as a sort of third language, these authors try to enforce alignment between encoder representations. So not agreements on the decoded representation, but agreements on the encoded side, which seem to work in their paper also pretty well. And there's also a cool study with Macro with a lot of experiments in a massively multilingual setup. Uh, they didn't focus specifically on zero-shot translation, but I think their experiments are pretty interesting. So I encourage you to look into that if you're interested. So what we try to do work, we try to incorporate a bunch of other auxiliary losses from language models to improve zero-shot performance. Maybe we didn't try hard enough, but it's slow. It's made the training slower, and we didn't see a significant effect, but it's maybe worth exploring further connection and maybe connect it back to other components of the machine translation and see whether agreement-based training can be compatible, can be further improved, or improve other methods that try to tackle the data side or maybe the architecture side of the system. I guess in my opinion, one of the open questions and exciting open questions from a multitask perspective is like, how do you not only learn these consistent models with fixed graphs of languages or fixed graphs of tasks, but how do you keep expanding, keep adding new languages, maybe new dialects, etc. And mathematically, the question is like, how do you convert a language model into like an unconditional physical probability distribution, right? When you have two unconditional probability distribution, how do you stitch them together in a sort of principled way? What kind of biases you can leverage in the data that would allow you to do that? So it's just an open question that I am not aware of any specific answers to, but there are architectures and other parts of the literature, machine learning, such as in computer vision. People looked into cycle GANs and they try to leverage this cycle consistency in order to sort of connect to these joint probabilistic models together. So maybe something like this could be done in language, and maybe yeah.
Um, can you comment on? Oh, thank you, Rusty. Can you comment on like potential applications to other domains? Like if the
Right,
graph is between two languages and the image, say multilingual captioning.
right. So I think that's definitely an interesting problem, and as the only like the in terms of the applicability of the method, we specifically target the loss. And loss is very architecture agnostic and data agnostic, right? So this is the way that you compute basically something that you're going to be optimizing with your optimizer, regardless of how your model is parameterized and what the architecture is. So as long as you can construct an architecture that sort of translates between images, let's say, and sentences, the only, I guess, tricky part would be that if you go from an image, to a sentence, maybe you don't want to go from a sentence to an image. Maybe you need to be able to translate between, different sentences and then also between image and the sentence. So once you figure out what kind of models and like how, what kind of components are there in the model, right, in the architecture, I think you can just take the loss and just apply and try to train the model on your data, and that should improve the zero shot consistency of the task. So if maybe the zero shot direction is from, let's say, images to captions in some foreign language, but you do have parallel data between images and captions in English, then this method could be applicable to that.
Okay. Gavin from audience also mentioned in your paper you mentioned style transfer.
Mm-hmm.
Could you elaborate more on that? What are some like potential ways of applying this to style transfer?
Right. I think yeah, style pattern transfer is also sort of new get a problem in natural language where you're trying to take a text in one style and then to sort of process it and output and generate text. The same text with the same meaning in the same language, but with a different style. And the style could be, let's say, you want to change the style of the formal language into colloquial and vice versa, right? Um, or maybe like from one dialect to the other. So it's very close to translation, in my opinion. It's you can think of a style as different language technically, and then the sort of the problem is very similar. So you could try, but the interesting part is that the number of languages is sort of limited and capped maybe to a few hundreds, maybe. Okay, so the number of languages in the world is around a few thousands, right? But no more than that. Actually looking at the problem that I outlined here, where you're trying to add new nodes to your graph, right? This may not be so practical if the number of nodes or number of languages is sort of limited. But the number of styles could be way more than that. And it would be interesting to see, you know, to look into style transfer as, a problem that puts this whole framework into a different regime where you have way more nodes in the graph and then you need to sort of be able to incorporate new styles as they appear in language.
Okay. Someone's asking, is the code available? I said because they're trying to find a GitHub repository.
Yep. I don't know. You guys are planning to link the slides somewhere, right? So I have a link on the yeah. So right now, I guess maybe if you can see in the left corner of the screen right now. But you can also Google my name, find my website. It's there. We do have the code available, so you can run the experiments and reproduce the data sets as well.
Okay, great. All right, we are at 1 o'clock mark, so we're technically we're running out of time. So uh, thank you, Marian. Thank you very much for the great presentation, and thank everybody for joining us on YouTube and Facebook. So, if you have any further questions, yeah, please uh, chat or chat in our Slack channel or um, send us email.
Perfect. Thank you for having me.
All right. Thank you very much. Okay. See you next time, everybody. Bye bye.
Bye.